Hey, welcome back. Today, we are cracking open the Chemist's recipe book to get a handle on a really core concept, formula mass. This is the amazing tool that lets us go from just looking at symbols on a page to making precise, real-world measurements. You know, have you ever wondered why taking care of a swimming pool is such an exact science? I mean, you can't just dump in a random scoop of chlorine or whatever. If you add too little, you get all sorts of gross stuff growing in there. But if you add too much, you get stinging eyes and you can even mess up the pool liner. It really all comes down to chemistry by the numbers. If you want to get the calcium level in your pool just right, for instance, you need a very specific amount of a certain compound. And to do that, you have to know exactly what's inside that compound and how much each of those little atomic ingredients weighs.
And that, right there, brings us to the main tool for the job. To solve our pool problem, or really any problem that involves mixing chemicals in the right amounts, we have to understand something called formula mass.
So what is it? Well, to put it simply, the formula mass is just a total weight of everything listed in a chemical formula. The easiest way to think about it is this. The chemical formula is your recipe, the atoms are your ingredients, and the formula mass, that's the total weight of all those ingredients added together.
And figuring it out follows a super simple three-step recipe of its own. First, we read the formula to see what we're working with. Second, we count up all of our ingredients, that is, the atoms of each element. And finally, we just add up all their individual masses to get the grand total. So, let's give it a try.
All right, let's put those 3 steps into practice. We'll start with something called covalent compounds. You can just think of these as substances that are made up of nice, neat, individual little packages we call molecules. Now, because the chemical formula for these kinds of substances represents one single self-contained molecule, you'll often hear chemists use a slightly more specific term here, molecular mass. It's calculated in the exact same way as formula mass. It's just a more precise name for this particular case. Let's use a real-world example you probably have in your medicine cabinet, ibuprofen, the stuff in Advil. Its chemical formula is C13H18O2. So, based on what we know, how do we figure out its molecular mass? Okay, let's break it down ingredient by ingredient. First up is carbon. The formula tells us we have 13 carbon atoms, so we multiply 13 by carbon's average atomic mass, and that gives us a total of 156.14 atomic mass units, or AMU for short. Next, we do the exact same thing for hydrogen. We've got 18 hydrogen atoms, so their total contribution to the weight comes out to 18.14 AMU. And finally, we have our 2 oxygen atoms. We do the math, and that gives us a nice, clean 32.00 AMU. Now for the easiest part, we just add it all up. We take the 156.14 from the carbon, plus the 18.14 from the hydrogen, plus the 32 from the oxygen, and we get a grand total molecular mass for ibuprofen of 206.28 AMU. See, it really is just like following a recipe. So that's how it works for those nice, neat little molecules. But what about a totally different kind of substance, like an ionic compound? You know, like the salt on your dining room table. The structure there is completely different. And here's the key difference. Unlike an ibuprofen molecule, table salt isn't made of tiny little NaCl units just floating around. No, it's this huge repeating crystal structure of ions. The formula, NaCl, just tells us the most basic 1-to-1 ratio in that giant structure. And that's why we call it a formula unit, and why it would actually be incorrect to call its mass molecular mass. But here's the really good news. Even though the structure is different, the calculation is exactly the same. For sodium chloride NaCl, we just add the average atomic mass of 1 sodium atom to 1 chlorine atom, and we get a formula mass of 58.44 AMU. Simple as that. Okay, but you might be thinking, wait a minute. Since we're dealing with charged ions, shouldn't we be using their masses instead of the neutral atoms? It's a great question, and the answer is actually pretty cool. You see, the mass of an electron is so incredibly tiny that it's basically negligible. But even better, that tiny bit of mass that the sodium atom loses when it gives away an electron is immediately gained by the chlorine atom that takes it. The mass just gets passed along, so for the whole unit, it all cancels out perfectly. It's a perfect little balancing act. So far, everything we've talked about has been on a microscopic scale, using these atomic mass units. But let's be real, none of us has a scale next to our swimming pool that measures an AMU. So how do we make this useful? How do we build a bridge from the world of atoms to our world? And this is where the magic happens.
A mole is just a word chemists use for a specific, really big number of particles. And because of the genius way the whole system was designed, the number we calculated for the mass of one tiny formula unit in AMU is the exact same number for the mass of a whole mole of those units, but measured in grams.
Just take a look at this. One single formula unit of salt has a mass of 58.44 AMU. A whole mole of salt, that's over 600 sextillion units, has a mass of 58.44 times grams. The number is identical. The only thing that changes is the scale, from the atomic to the human. It is an incredibly powerful and convenient trick.
This simple calculation is the bridge. It's what connects the invisible world of atoms and molecules to the tangible world of grams that we can actually measure out on a scale. This is how a chemist can weigh out a pile of white powder and know with total confidence exactly how many atoms they're holding in their hand.
And that brings us right back to our swimming pool. We now know how to figure out the mass of a single recipe unit and, more importantly, how to translate that into grams we can actually weigh. So the final question is, what's the next piece of the puzzle you would need to figure out exactly how to dose that entire pool? We'll leave you to think on that. Thanks for joining.